MRI machines are indeed marvels of modern engineering. Here's a glimpse into the intricate design and functionality of these remarkable devices. 1. Magnetic field generation. At the heart of every MRI machine is a superconducting magnet. This magnet generates a powerful uniform magnetic field, typically ranging from 0.5 to 3 Tesla, or even higher in some research-grade machines. The magnet is usually cooled to cryogenic temperatures using liquid helium to maintain its superconducting state. 2. Gradient coils. Surrounding the magnet are gradient coils, which produce varying magnetic fields in different spatial directions. These gradients are essential for spatial encoding, allowing the MRI machine to differentiate between different tissues based on their magnetic properties and location. 3. Radio frequency coils. RF coils are used to transmit radio frequency pulses into the patient's body and to receive the resulting signals. These coils are carefully designed to maximize signal sensitivity and spatial coverage while minimizing interference. 4. Patient table. The patient lies on a movable table that can slide into the MRI machine. This table is often equipped with various adjustments to ensure the patient's comfort and proper positioning within the magnet's bore. 5. RF shielding. MRI rooms are heavily shielded to prevent external radio frequency interference from affecting the imaging process. The shielding typically consists of layers of conductive material to create a Faraday cage, effectively blocking external electromagnetic fields. 6. Gradient and RF amplifiers. These components amplify the signals generated by the gradient and RF coils, ensuring that they are strong enough to produce high-quality images. 7. Control system. The MRI machine is controlled by a sophisticated computer system that coordinates the operation of the magnet, gradient coils, RF coils, and other components. This system also processes the raw data collected during the imaging process and reconstructs it into detailed images. 8. Safety systems. MRI machines are equipped with numerous safety features to protect both patients and operators. These may include emergency stop buttons, temperature monitoring systems for the magnet coolant, and automatic shutdown mechanisms in case of equipment malfunction. 9. Advanced imaging techniques. In addition to standard imaging sequences, modern MRI machines may offer a variety of advanced techniques such as diffusion-weighted imaging, perfusion imaging, and spectroscopy. These techniques provide valuable information about tissue structure, function, and metabolism. 10. Gradient coil design. The gradient coils are meticulously designed to produce precise and uniform magnetic field gradients across the imaging volume. Achieving this uniformity is crucial for accurate spatial encoding and image reconstruction. 11. Cryogenic system. Maintaining the superconducting magnet at cryogenic temperatures requires a sophisticated cryogenic system. This system not only cools the magnet, but also manages helium levels, ensuring long-term stability and reliability of the magnet. 12. RF pulse sequences. MRI sequences involve precise timing and coordination of RF pulses, gradient switching, and signal acquisition. Advanced pulse sequence design plays a critical role in optimizing imaging parameters such as contrast, resolution, and scan time. 13. Parallel imaging. Parallel imaging techniques exploit the spatial sensitivity of multiple receiver coils to accelerate image acquisition. These techniques require complex reconstruction algorithms to combine data from multiple coils and generate high-quality images. 14. Artifact correction. MRI images can be affected by various artifacts, such as motion artifacts or susceptibility artifacts caused by magnetic field inhomogeneities. Sophisticated algorithms are employed to correct these artifacts and improve image quality. 15. Safety protocols. MRI machines must adhere to stringent safety protocols to ensure the well-being of patients and staff. This includes screening for contraindications such as implanted medical devices or metallic objects, as well as implementing safety measures to mitigate potential hazards associated with strong magnetic fields. 16. Integration with other modalities. In some cases, MRI machines are integrated with other imaging modalities such as PET or CT to provide complementary information for more comprehensive diagnosis and treatment planning. This integration requires seamless coordination of imaging protocols and data fusion techniques. 17. Research and development. Continuous research and development efforts drive innovation in MRI technology, leading to advancements such as higher field strengths, faster imaging techniques, and novel applications in areas like functional MRI, fMRI, for studying brain function, or MRI-guided interventions for minimally invasive procedures. These additional aspects underscore the depth of engineering expertise and innovation involved in the design, construction, and operation of MRI machines, making them indispensable tools in modern healthcare.